What is a spectrum? That whenever you, for example, you have white light, you pass this through a prism, and then you get a spectrum, a continuous spectrum of light. Okay, so this is the impression. This is the impression, right? This is the impression of the white light when passed through a prism. So please write the impression produced. Produced the screen when any light is passing through prism is called spectrum. It's called spectrum. Now, spectrum, as you have seen, it is of two types, right? It is of two types. It is continuous and it is discontinuous. So we will write the spectrum. Spectrum are of two types. One is known as continuous. This is the correct continuous. And the other is discontinuous. The continuous spectrum and discontinuous spectrum. What is the feature of continuous spectrum? In which all the wavelength of radiation, they lie between two extreme wavelength, and they are continuous. There are no gaps, right? The first point is that there will be no gaps. No gaps between start and end. Right? All wavelength lie between the two extremes. An example will be with GO produced by when is the FGR produced? When we splitting by the splitting of white light. By the splitting of white light. Okay. Now this continuous spectrum, they will have gaps between start and end. Right? All wavelengths are not present between the extremes. Between the extremes. Okay. Now one more example is that you can write is rainbow. Rainbow is also a continuous spectrum. It is also a continuous spectrum. For example, here you can write hydrogen spectrum. Or any atomic spectra. Any atomic spectra. Write this down. Let me know if you're done.
Done, sir.
What about Mariam? Or was this
Done,
Mariam?
sir.
Okay, Mariam is also done. Okay. Now write the atomic spectra. atomic spectra. What is atomic spectra? Now, this continuous spectra is known as the atomic spectra. Okay, atomic spectra is the discontinuous DC spectra produced by an atom. Produced by an atom. Okay, produced by an atom. Atomic spectra are of two types. They are of two types. Number one is known as the emission spectra. Emission spectra. Okay. Now, how this emission spectra that will be absorbed? Whenever you have an excited body, the radiation electromagnetic waves are emitted by an excited body, that leads to emission spectra. Okay, for example, this is your body. It is highly charged. It is excited body. It has high energy. Whenever there is high energy, it will be emitting some radiations. It will be emitting some radiations. And now you can have prism, or you can also have what? That grating kind of plastic that we saw in the video. You can also have that, but it is essentially working as a prism. Then you have the screen. Now, whatever you saw, that was the example of emission spectra. You had the hydrogen, it was very excited. The hydrogen atoms were excited due to the large potential difference, the large voltage which was applied in the discharge tube. Now, as the hydrogen were excited, they were emitting some radiations. Now, those radiations, they were of some color. You will have, for example, red. Okay, you can have yellow, you can have orange, and with GO, you can have some blue and indigo colors, right? So this is an example of emission spectra. This is an example of emission spectra. Please write this down. Let me know if you're done.
Yes, sir.
Now, second is the absorption spectra. Absorption spectra. Absorption spectra. Now, this is a bit conceptual that you have to understand. This is a bit conceptual that you have to understand. Okay. Now, we have a source. Okay. Let us have a source that I'm. How to make a bulb like this? A torch kind of thing. I want to make a torch kind of thing. Okay. Now this source is giving some electromagnetic radiations, and all these electromagnetic radiations, let us say that they lie between what? They lie between red and violet, right? Red and violet. That means they have with GO. So what you are doing? You are radiating electromagnetic radiations. The source is emitting the electromagnetic radiation of violet, indigo, blue, green, yellow, orange, and red color. All of these colors. Okay, all of these colors. Then you have a body here. Okay. Now, what will happen? Will the body absorb all the radiation that you are giving it to? No, it won't absorb all of it. It will absorb some distinct electromagnetic radiations, which will correspond to the difference in the energy levels. For example, difference in energy level is, now this difference is something, let us say, for example, for violet, right? So you have the electron here, then you will, if this gets the violet light, the electron will jump over to the next level, okay, to the next level. But this electron, it won't absorb if you give it blue light. So this electron will not be absorbing anything if you give it blue light, because the next destination for the electron lies in the violet range of electromagnetic radiations. So there will be a few things that there will be a few radiations that this particular object it will absorb, and few will be left. Okay, so let us assume that some of them are left like this, and then you put up a screen, so it will absorb everything, and some will be left. For example, you have been left with green, and let us say you are left with blue, left with red or something. Okay, and the rest of the screen it will be black. So what is happening? Let us write that in words also, so that you may remember it in your notes. First thing that is happening is, what is happening now? When an atom is irradiated by electromagnetic wave of by a range of electromagnetic waves. Okay, as we are having this range from violet to red, this is the range of electromagnetic waves, and we are irradiating. That means we are striking a particular atom with this range of electromagnetic waves. When an atom is irradiated by a range of electromagnetic waves, not all waves are absorbed. Only selected waves are absorbed, and the rest are transmitted. Okay, and the rest are transmitted. Now, those the waves that were not absorbed by the atom strikes on the forming absorption spectra. Forming the absorption spectra.
Sir,
Yes, yes, tell me.
irradiated means striked.
Yeah, strike.
Okay, sir. Done, sir.
Both of you?
Yes, sir.
Okay. Now, this is the emission spectra, absorption spectra. Now we should come to the point, that is the hydrogen spectrum. The hydrogen spectrum. Okay. Now, You have seen the hydrogen spectrum, right? In the video. Now we will just define whatever was happening in that video in words. Then we will look at a few conclusion points. Okay. So please write with me. Nitrogen spectrum is produced by the transition of cited electrons at higher levels to the lower levels to the lower levels. Okay. Now, whenever there is a transition from higher to lower level, that means you will be emitting some radiation. That is why hydrogen spectrum is a emission spectrum. It's an example of emission spectra. It's an example of emission spectra. Now, whenever you will have the hydrogen spectrum, there will be many radiations that will be emitted. Okay, a number of radiations are observed during the transition of electron from higher to lower energy levels. From higher to lower energy levels, right? Now, all of these lines or the radiations the lines the lines observed by these transitions are grouped in 5 series. Are grouped in 5 series. Your first time examinations will be MCQ.
Yes, sir.
Yes, sir.
Okay. Do you have NCERT exemplar? No, never heard of it.
No, sir.
No, sir. Sir, like question banks.
Okay, what question bank are you using?
Together with.
Together with. Okay,
Yeah.
you can use in together with. You can see that if you have MCQs now, they will be saying that these questions are from NCERT examples. Have you ever solved those together with questions?
Yes, sir.
You have seen NCERT exemplar?
Yes, sir. Yes, sir.
Right? Okay, fine then. Most of the guides, whatever question bank that you have, they will have those NCERT exemplar questions also. But it will be good if you have those NCERT exemplars with you also. They are available in the NCERT website for free, the PDF versions. NCERT exemplar. This is class 11th, right? Okay. So if you go to this site, there you will see a tab kind of thing. There you will have from class 6 to class 12, you will have the NCERT exemplars chapter wise. Okay, you'll have chapter wise. So download whatever you want. They are in English and Hindi both. So you must be downloading for the English one only. And will your school also holding those case-based questions? Yes or no?
Yes, sir. Yes, sir. They are.
There are case-based also. Okay, fine. I mean, trying to at least have a look over the exemplar questions. Okay.
Yes, sir.
Let me know if you're done writing this. Are you done?
Done, sir.
Done. Okay.
Done, sir.
Now, those 5 series, what are those 5 series? So first of all, let me give you the picture on what happens. Copy image and paste. As you can see here, let me get, yeah. So if you see this first line, that is the Lyman series. Okay, this is the Lyman series. What is the thing which is common with all of these lines that you can see? All these lines that you are seeing now, the violet kind of lines. What is common for all these lines from infinity to 2? Can you see anything common in the Lyman series, in the Balmer series, Parsons series, bracket, or Pfund in these 5 series? I mean, there is nothing common between Lyman and Balmer, but all the lines of Lyman, they have something in common. All the lines of Lyman series, they have something in common.
They increase by one number.
No. Okay, they increase by in one number. Okay, so first thing is that how are you looking at it? Are you looking from downside from 1
No, sir,
to
from
above?
up to down.
From up to down.
From
Okay, so first
Pfund,
series.
yeah.
Okay, so you're starting from Pfund. Okay, fine. Let us start with Pfund. So in Pfund, if you have the initial stage for this line, what is the initial? Where is the electron initially?
7.
No, it is in
8.
infinity, right? Infinity. This is infinity. That means n can be of any number. Okay, from 7, 8, 9, 10. N can be of any number. Okay.
Yes, sir.
So initially this here is infinity. And what is the final? Final is
5.
5.
5. Very good. What about this one? Both of you tell me what is the initial?
Initial is 7.
7. Final is
Final is
5.
5.
5. Very good. What about this? What is the initial?
Initial is 6. Final is 5.
Final is 5. Right. So this is something common, right? In all the lines of Pfund series. Yes or no? That the final stage for the electron, the n final, the principal quantum number or the final shell for the electron will be 5. For bracket, what will be the n final? What will be the final n?
4.
Yeah, very good. What about Paschen?
3.
N final, 3. What about Balmer?
2.
2.
And for Lyman?
1.
Yes, and final is equal to 1. So these are the 5 series. Okay, these are the 5 series. We write the names. The first one is Lyman series. Ikra, how are you? You joined quite late. What happened? Did you forget about the class?
Good evening, sir.
Good evening.
Sir, I am tired after college, so
You're in college.
yes, sir.
You call it college.
Yes, sir.
Acha. Okay. Okay. So they call it college there. Junior college. Yeah.
Yes, sir. Pre-university college.
pre-university college. So Lyman series, and this Lyman series, it lies in the range of UV range, okay? The ultraviolet range, okay? All these lines that you will get, it will be in the UV range. Second is, after Lyman is Balmer series. The N final for this is 2. This is only in the visible range. Then the third is Boston series. The N final is equal to 3. It is present in the infrared region. Infrared. Fourth is bracket. The N final here is equal to 4. It is also in the infrared region. Fifth is P fund series. The N final is equal to 5. This is also in the infrared region. This is also in the infrared region. So you just have to remember about the final position of the electron, the final shell of the electron. The initial can be anything greater than the N final. So for Lyman series, the N final will be 1. The initial can be 2, 3, 4, 5, 6, and so on. Okay. And similar is the case for Balmer-Parsons bracket and P fund.
Answer.
Everyone done?
Yes, sir.
Yes, sir.
Okay. Now, there is a relationship between whatever wavelength you get and what are the initial and the final stages. Okay, initial and the final stages. So the relationship is given by 1 upon lambda. 1 upon lambda. In this 1 upon lambda, you must remember that it is the wave number, right? Wave number. 1 upon lambda is equal to RH, that is a Rydberg constant, into Z square 1 upon N1 square minus 1 upon N2 square. Okay, 1 upon N1 square upon 1 upon N2 square. Now, what are the terms? What are the terms? You know what is wave number, right? That is 1 upon lambda. What is lambda? Lambda is wavelength. Lambda is wavelength. Then what is RH? RH is known as the Rydberg constant. RH is known as the Rydberg constant. Then the next term is Z. What is Z?
Atomic number.
Yes, very good. The atomic number, the number of protons. Please write everything. What is lambda? It is wavelength. Then what is RH? It is Rydberg's constant. Okay, the Rydberg constant, its value is, please write the value for Rydberg constant, 109677. Then you have Z. This is the atomic number. Then you have N1. N1 is the lower orbit, okay? Lower orbit. N2 is the higher orbit. And this lambda, it will be in terms of length. So whatever term, whatever answer you will be getting from this, they all will be in centimeter inverse. Lambda in centimeter inverse.
Done, sir.
Done, all of you?
Yes, sir.
Yes, sir.
So please write a question. Calculate the wavelength of first line . of Lyman series in He plus spectrum. In He plus spectrum. Okay. So this first line of Lyman series is important. Okay. The first line of Lyman series is important. Why? See. Answer. So if you have first line, that means whenever you will have Lyman series, the n final will be what?
One.
Yes. And n initial can be 2,
Infinity.
3, 4 till infinity, right?
Yes, sir.
Yes. So the first line that will be made by the Lyman series is transition from second to first, right? It will be from second to first. Yes or no?
Yes, sir.
Right? It will be from second to first. That is why this is known as the first line of the Lyman series. Then from 3 to 1, this will be second line. Then from 4 to 1, this will be the third line of the Lyman series. So now you know the transition. You know the transition. So you know the transition, that is the transition is taking place from 2 to 1, right? From 2 to 1. Now what you will do, you will write the formula, that is 1 upon lambda is equal to RH Z square. Okay, please remember that it is atomic number Z. Okay, divided by 1 upon, then you have the N1 square minus 1 upon N2 square. After that, what is RH? RH is equal to how much? Tell me. RH is equal to
109677.
yes, 109677. What is Z?
1.
Helium, na? See, helium spectrum. So from here you
Okay.
will get the Z. Yeah, now it will be 2. Very good. 2 square into 1 upon N1. N1 means lower. Okay, 1 is lower, so N1 is always lower. N2 will be higher. Okay, lower and higher. N1 lower, N2 higher. What is the lower? 1 square minus 1 upon, what is the higher one?
2.
2 square. Okay, so please solve this. So this 109677 into 4 into 1 minus 1 by 4. So this will be 3 by 4, I guess. This will be equal to 109677 into 4. 1 minus 1 by 4, it will be equal to 3 by 4. So you will this 4 and this 4 will be cancelled, and you will have 1 upon lambda is equal to 109677 into 3. So that implies that lambda is equal to 1 upon 109677 into 3. Whatever you will be getting in terms of centimeters. Okay, you will be getting in terms of centimeter, because here it is centimeter inverse. It is centimeter inverse, centimeter inverse, and centimeter inverse. But when you have lambda, it will be reciprocal. So reciprocal of centimeter inverse, it will be equal to centimeter.
Done, sir.
Then all of you?
Done, sir.
Yes, sir. Done.
Then write the next question. Calculate the, let us talk about wave number. Okay, 1 upon lambda. Calculate the wave number of last line of Parston series in helium positive spectrum. Okay, so solution. First thing that you will identify is what series is this? Parston series. So in Parston series, n final is equal to, in Parston series, n final is equal to 3. Very good.
3.
n initial will be equal to 4, 5, 6, 7 till infinity. So tell me, what will be the last line of the partial series?
Infinity.
Yeah, very good. So last line will be infinity to 3. Okay.
3.
So you are starting from n is equal to infinity to n is equal to 3. N is equal to infinity to n is equal to 3. So also one more thing that you should do is you should write the z. What is the z here? What is the z?
2.
Very good. Z is equal to 2. Okay. Now this is easy. So you have 1 upon lambda, or the wave number is equal to, what is that, RH into z square multiplied by 1 upon n1, which is smaller. So what is smaller between infinity and 3? Smaller is 3, right? Minus 1 upon infinity. You don't have to do anything because 1 upon infinity will be equal to 0. So RH z square is equal to 4 by 3. This is the wave number. Okay, this is the wave number, right? 4 by 3, na?
Yes, sir.
No, we did a mistake. This will be squared, na? This will be 4 by 9.
Yes, sir.
N square will be there, na? So it will be 4 by 9. And we will get this answer in terms of centimeter inverse. You just have to multiply the value 109677 and you will get the answer. This is very important. Most of the students, they mistake here. Okay, so you have to look at what is the what ion is there, what atom is there. You may also have, you will have any atom which has only one electron. So you will have hydrogen, you can have helium positive, you can have lithium 2 positive, you can have beryllium 3 positive, and so on. Okay, you can have any atom, but there will be only one electron. But that doesn't matter to you. What matters is the atomic number. Then
Yes, sir.
yes.
Yes, sir.
Yes, sir.
All right, then now write the next topic, that is De-Broglie hypothesis. De-Broglie hypothesis. Okay, De-Broglie hypothesis. He came and he gave the wave nature of electron. He gave the wave nature of electron. If you can remember, we started with the photoelectric effect, and from the photoelectric effect, we concluded with the Bohr's model. Now, from the Bohr's model of the atom, De-Broglie extracted the idea that the electrons, they have wave nature. Please remember that in photoelectric effect, we started with the particle nature because one of the waves, one photon, is giving out only one electron, right? So from there, we were thinking about the particle nature of electron. Right now, De-Broglie, from the Bohr model of atom, he gave the wave nature of electron. So please say the first point regarding the De-Broglie hypothesis is that it gives the wave nature of electron. Now De-Broglie, he hypothesized that if anything is in motion, that means it would have a wave associated with this. It will have a wave associated with this, right? According to this hypothesis, anything in motion should have a wave associated to it. This wave is known as De-Broglie wave. This wave is known as De-Broglie wave. Okay. How did he come to this conclusion? The mathematics that he had was very easy. He said that we have two equations. He said that we have two equations according to Planck. He said, according to Planck, the energy of a photon is equal to hc upon lambda, right? Hc upon lambda. He also said that according to Einstein, we have the energy, it is equal to m into c square. That is the speed. Okay, that is the speed of light. The energy of photon, he said, according to Planck, is equal to hc upon lambda. Energy of photon, according to Einstein, is equal to mc square. He said that I can equate both of these things. So he said, okay, fine. You will have mc square. You will have, or rather, we can say hc upon lambda is equal to
mc square.
Yeah, mc square. Now what we will do, we will eliminate the c and we will eliminate the square here. And from here we can get that lambda is equal to lambda. If I go lambda there, this will be equal to Planck's upon mc, right? Planck's
Yes,
constant upon mc. Now you can see that anything which has a mass, now this is all about photons, right? This was all about photons. Why did he extended this to any mass, okay, to any object other than photon. So for any object with mass m and velocity v, he said that the wavelength of that object will be equal to h upon m into v. Okay, so please write this down.
Done, sir.
Done? All of you done?
Yes, sir.
Okay. Now, from here, you can also calculate the relationship between the wavelength and also the kinetic energy. Okay, wavelength and the kinetic energy. So we can write wavelength, relation between wavelength and kinetic energy. What is the relationship? Here we have lambda, it is equal to h upon mv. Now, mass into velocity is equal to momentum. Yes or no?
Yes, sir.
I can write momentum is given by p. Now, there is a relationship that you must have learned in the physics, that kinetic energy is equal to half mv square is equal to half mv square. Now, 2 times kinetic energy, it will be equal to mass into velocity square, right? We have multiplied 2 in that side of the equation. Now, from here, we can also write that 2 into mass into kinetic energy. By multiply this part of the equation, this whole left hand side and the right hand side with mass, it will be equal to m square v square. Now, this m square v square is equal to momentum square. It is equal to 2 into the mass into the kinetic energy. Okay? That is why momentum will be equal to how much? It will be equal to under root 2m kinetic energy. Okay. So from here you can write lambda is equal to h upon under root 2m kinetic energy. Okay. So do you guys remember this this relationship from physics or no? You forgot it.
Yes.
You remember it, right? Okay, fine.
Yes.
Done, sir.
All of you done?
Yes, sir.
Now we will derive the Bohr postulate, that Bohr said that the angular momentum is the integral multiple of nh upon it is the integral multiple of what? Nh upon 2 pi, right? Whatever the angular momentum is, it is the integral multiple of h upon 2 pi. So we will derive that from this De-Broglie's postulate, okay, from this De-Broglie's hypothesis. Now, I will explain first and then you can write it. So whatever the nucleus is, electron should be orbiting in a orbit or a shell like this, okay? In circular kind of shell like this. Right? This is what Bohr said. So what Bohr said. So what will be the circumference? What will be the circumference? 2 pi r,
Yes, sir. 2 pi.
right? 2 pi r, okay? Now 2 pi r. This 2 pi r, it is the whole length of the electron that is just traveling. Now, in terms of wavelength, how many wavelengths will it be covering? How many wavelengths it will be covering? For example, if it is in the first orbit, it will have one cycle. It will have how many cycle? One cycle, right? One cycle means, if you remember from the waves, we have, so from here to here is one cycle. Yes or no?
Yes,
This is
sir.
complete one cycle, right? And this is also in terms of length, it is equal to how much? It is equal to 1 lambda, right? This
Yes,
is also
sir.
1 lambda, right? 1 lambda. Now, similarly, if you are in the first orbit, you will have one cycle. That means you will have 1 lambda. If you are in the second orbit, you will have you will be completing 2 cycles. That means it will be 2 lambda. In third, you will be completing 3 cycles. That is 3 lambda. Similarly, for example, if I say this is the third orbit, then the electron will be having this kind of wave, you can say, like this. Okay, so this is the kind of trajectory that electron should be following. And as you know, from here to here, it is equal to 1 lambda. This is 2 lambda. From here to here, it is 3 lambda. Okay, so this whole circumference that will be covered by the electron, it is equal to how much? 3 lambda.
3 lambda.
Right? 3 lambda. Now, in a similar way, what we can say is that if we are in the nth orbit, for electron in nth orbit, 2 pi r is equal to n lambda. 2 pi r is equal to n lambda. Then 2 pi r is equal to n h upon mv. From here, lambda is equal to h upon mv. So here it is 2 pi r is equal to n h upon mv. Okay, so lambda is equal to h upon mv. This is from De-Broglie. Okay, this is from De-Broglie. Now you can see it is very simple. We will substitute this mv there. So mvr is equal to n h upon 2 pi, right? This is equal to nh upon 2 pi. This is mv is momentum. Have you learned rotational motion, angular velocity, angular momentum, these things? No?
Yes, sir.
You have learned it. So whenever you multiply any, for example, you have velocity into r perpendicular, it is the angular velocity. Momentum, it is mv into r perpendicular, the distance or the radius, it is equal to angular momentum, right? So here, what is mvr? Mvr is the angular momentum. Which is equal to n is the integral multiple h upon 2 pi. Here n should be equal to 1, 2, 3, and so on. Okay, and will be equal to all these things. Now, according to Bohr and according to De-Broglie, this n here, it meant different thing. So according to Bohr, n is equal to shell number, right? N is equal to shell number. But according to De-Broglie, n is equal to number of waves. N is equal to number of waves. Okay, so you can write from here, for electron in nth orbit, 2 pi r is equal to n lambda. Maybe you can make this also, right? Make this first. Make this. And I'm very sorry for the
Done,
kind of
sir.
waves that I've. Okay, I've drawn this. Okay.
So can you scroll up?
Yeah, sure.
Yes, sir. Done. Done, sir. Can you scroll down?
Down.
Done, sir.
Now, write a few questions. Okay. Question, please. Right. What is the maximum number of emission lines when an electron of hydrogen atom in sixth orbit drops to the ground state? Okay, so we have in n is equal to 6. Okay, in n is equal to 6. Now please remember, if we make the lines here, so sixth how many is this? This is 1, 2, 3, 4, 5, and 6. Okay, 5 and 6. Now see, you can have many transitions. Okay, you can have many transitions that can take place. For example, you are in n is equal to 6, right? You are in n is equal to 6. Now from n is equal to 6, you can make transitions that are directly to 1. Let's start from here. You can go from 6 to 5. Then you can go from 6 to 4 also. Then you can go 6 to 3. After that, 6 to 2. And after that, you can also go directly from 6 to 1. Okay. So all these are probability. All these things can happen, right? Yes or no? Tell me.
Yes, sir.
Right. All these things can happen. Now, if you are in 6, that can happen. But you have to reach the ground state, right? You have to reach the ground state. That means if I go from 6 to 5, the process is not complete yet. The process is not complete yet. That means when I get to 5th, then I can have these. Change the color. Then I can have these kind of transitions. Yes or no? If I get to the 5th one.
Yes, sir.
Now, if I get to the 4th one, now you can imagine what are the lines that can happen. What are the lines?
Yes,
Now
sir.
we can make a pattern. Okay, we can make a pattern. For example, if I am in the 6th orbit, I will have 1, 2, 3, 4, 5 lines. If I am in the 5th orbit, I will have 1, 2, 3, 4 lines. Okay, so in the 6th, I will have 5 lines. N is equal to 5. I can have 4 lines. N is equal to 4. I can have 3 lines. N is equal to 3. I can have 2 lines. And N is equal to 2. I can have how many lines? 1 line. But obviously, if I am on the ground 0, I cannot produce any further lines. So this will be the total. Can you add this up? This should be equal to 15. Yes. Is this 15?
Yes, sir.
Yes, this is 15. I can also write a formula. You can calculate the maximum number of emission line. Maximum number of emission lines is equal to n into n minus 1 divided by 2. As you can put here, 6 into 6 minus 1 is equal to how much? 5 by 2, it is equal to Okay, so were you able to copy this?
Yes, sir.
Yes, sir.
Okay, you were able to. Okay. Is my voice clear or is it lagging now?
Clear,
Or is
sir.
it fine? It is clear. Okay. Please write question. Calculate the wavelength of an electron moving with velocity into the power 7 meters per second. 2.05 into 10 to the power 7 meters per second. How will you solve this? You will write the according to De-Broglie equation. What is the De-Broglie equation? It says that wavelength is equal to h upon m
MC.
into v. mv, right? mv.
Yes.
So you have all the things. So, but you know the Planck's constant. I will not give the Planck's constant, but I will give you the mass of electron. Okay, mass of electron is equal to, please write, 9.1 into 10 to the power minus 31 kgs. I'm not speaking. I've given you a question now. You have to do this and tell me the lambda. Okay, Mariam? Can everyone hear me?
Yes, sir.
Okay, Mariam is not able to hear me.
Sir, I can hear you now.
Okay, you can hear me now. Calculate the lambda and tell me the answer. No, calculate the lambda and tell me the answer. If you want any values, for example, for Planck's constant, the velocity is given. If you want the value of Planck's constant, then first you look in the copy, and if you cannot find that also, then we can provide you with the Planck's constant.
So what is H? I haven't written anywhere.
You haven't written anyone. Planck's constant E is equal to hc upon lambda. You haven't written.
No, no, sir. Planck's constant.
H is equal to 6.626 into 10 to the power minus 34. It is joules second, right? It is equal to joule second, but joule is equal to kg meter square, and then second is just second. Planck constant is joule second.
Okay, sir.
When you have kg meter square, then this will be second inverse, but this will be kg. Okay, Mariam has got the answer. It's in meters. Yeah, it's in meters. Yeah, correct, Mariam. Lambda will be equal to h, which is 6.626 into 10 to the power minus 34 kg meter square per second. Mass of electron is 9.1 into 10 to the power minus 31 into, this is in kg, into, then you will have the velocity. It is given as 2.05 into 10 to the power 7 meters per second, right? Meters per second. So you can cancel this kg with kg, this meter with this meter, and the second inverse with the second inverse. Now the next thing that we will do is we will separate the exponents and the numbers. So you will have 6.626 divided by 9.1 into 2.05. Then multiplied by 10 to the power minus 34 into minus 31 will go above, and this will be 10 to the power 31 into. Then you will have 10 to the power minus 7. 10 to the power minus 7. Now this will be equal to 6.626 divided by 9.1 into 2.05 into, this will be 10 to the power how much? You will get minus 10. Yes.
Yes, sir. 10.
Right. So we
Yes,
have
sir.
just meters left here. So just meters will be left here. This will be meters. Now you have to solve this 6.626 into 9.01, 9.1 into 2.05. So maybe I can do some kind of approximations. Yeah, I can do some kind of approximation to see. If I write this as 6.6, okay, divided by 9 to the 18. Okay, so much of approximation, 10 meters. Then this would be equal to, you have 18 and 6.6, right? So this will be 1.1 divided by 3. This is 3, 3 is 9. So 3 point, then you will get how much? From 9 you get 2. So you'll have 0, 3.6. This is equal to 3.6 into 10 to the power minus 10 meters. Okay. So approximately speaking, this is somewhat correct answer because the exact answer is 3.55. We have done some approximation and we got this as 3.6. Okay. So whenever you are having this kind of problem now, आप ऐसे छोड़ मत दीजिए कभी भी. Okay, don't leave those problems. At least solve for the exponents. You'll solve for the exponents. Now once you solve for the exponents, things very easy after that. Okay, so 6.626. If you are seeing 9.1, you can take this 9.1 as 9. You can take this 2.05 as 2. Then you can see that, okay, fine, if I get 18 and 6.6, then I can simplify it very easily without much approximation, because 6.626, right, and 6.6. This is not much approximation. We are doing approximation of 0.01 level. We are doing approximation of 0.01 level. Okay. So, and how to do what kind of approximation, where should we approximate, that you will come to know only after practicing a lot of questions. Okay. You will come to know only after practicing a lot of questions. Now, please write one more question. Similar. Okay. Similar question. Right. A tennis ball of mass 6 into 10 to the power minus 2 kg is moving with speed of 62 meters per second. The speed of 62 meters per second. Calculate the wavelength of ball. Okay. So how will we do this? According to De-Broglie equation, lambda is equal to h upon mv. Right. So you have the mass, you have the Planck's constant, you have the velocity also. Please calculate this fast. Okay. Please calculate this fast. Okay, Mariam, let us see. You didn't multiply? Okay. Six twos are 12, 606 and 17. This will be approximately equal to 0.0178, 0.0178 into 10 to the power minus 32 meters, which will be equal to 1.78 into 10 to the power
So up
1
to
into
how
minus
many
34.
decimal places should we find?
See, what I have seen is that uh, you should have two non-zero numbers after the decimal place. Okay, if you
Okay.
for being in the safe side, two non-zero after the decimal point. Done? Done, yes or no?
Yes, sir.
Yes, sir.
Sir, if we leave it as 0.0178, will that answer be also okay?
Yeah, that answer will also be correct. Okay,
Okay,
but
sir.
see, there are a few things that you should keep in mind. Do you think good handwriting gives you good marks? It may
Yes.
help you, right?
Yes.
Similarly, this is the notation. See, whenever the questioner, I mean, questioner, yeah, if someone is checking your paper, they will have the list of answers, okay, with them. They will have the list of answers with them. So first of all, what they will do is they will check the answers that you have written, and most of the times those answers will be in the form of scientific notation. Okay, they will be in the form of scientific notation. So there will be a degree of comfortability. There will be a degree of comfortableness with the questioner when he or she is checking your paper. If it is in the scientific notation, if it is in a good handwriting, but obviously in MCQs it doesn't matter. But in MCQs you will be given the answer in whatever terms. You will have just the four options, right? And you won't be
Yes, sir.
having this option as A and this option as B, right? You won't be given these options. So best is to give the answers in scientific notation with a good
Okay,
handwriting
sir.
if it is a subjective paper. Okay. Uh, right. Bohr's limitations of Bohr model. Please write. First point is that it is only applicable for it is that we should say not applicable for multi-electron system. It is not applicable for multi-electron system. Second thing, doesn't explain finer details of hydrogen spectra. Third point, please say it doesn't explain the effect of magnetic field the spectrum of atoms or ions. Okay, atoms or ions. So the effect of magnetic field on the spectra of atoms and ion, these are known as Zeeman effect. Okay, Zeeman effect. What is it? Didn't explain. It didn't explain the effect of electric field on spectra of atom or ions. This effect of this electric effect on the spectra of atom or ions is known as Stark effect. They are known as Stark. Fifth point is that. Now we also know that Bohr's theory could not explain anything about the shape of molecules or anything regarding the bonding of atoms. Okay, it doesn't explain regarding bonding of atoms.
Done, sir.
Need to account the wave nature of electron, which was given by De-Broglie. Done, everyone?
Yes.
Yes, sir.
So writing the last
Okay.
point.
Last point, just one correction. This is Stark, does not have E here. Okay, it is just Stark.
Done, sir.
Now we are almost at the end. That is the Heisenberg's uncertainty principle. Before going into Heisenberg uncertainty principle, let us understand how should we understand Heisenberg uncertainty principle and how should we relate to it. So Myra, tell me, can you see anything in a dark room if there is no light? Can you see anything in a dark room if there is no light? No, you cannot see anything if there is a dark light. That means if you are going to observe anything, for example, this is a microscope, okay, and from here we are going to observe a particular electron. Electron is in the orbit and the electron is moving. Okay, the electron is moving, and we expect that. Let me make the orbit. So let us say this is the orbit, and this is the microscope, and let us imagine that our electron is somewhere here. Okay, somewhere here. That means we are expecting it to follow this trajectory, that is the bold circular line. Now we want to see where the electron is when it comes here, but to do that we have to show some light. We have to have some kind of light. Now what happened? The light came and it struck on this electron. As soon as it struck on this electron, what happened? This electron, it changed its trajectory to somewhere else, right? Because this photon will have some energy, and this energy will be absorbed by the electron, and the electron will change its trajectory. It will change its trajectory. That means if we knew about the energy, if we knew initial energy, right, the kinetic energy, that means when we knew about the kinetic energy, we expected this path that electron should be traveling. So we knew the energy, but as soon as the position of the electron is distracted with photon, the photon was absorbed, the energy changed.
So your voice is breaking.
My voice is breaking. Okay, how's it now?
Yes, sir, it's fine now.
It is fine now, right? Now, this is what I was saying, that when we knew about the energy, and after that, we wanted to know about the position. As soon as we wanted to know about the position, we strike it with light. That light interacted with the electron, it absorbed it, and the energy was also changed, right? So when it struck the electron, we knew the position. Now, when we knew the position, the energy is impossible to determine the exact position and velocity of a moving electron. It is impossible to determine the exact position and the velocity of a moving electron simultaneously. Okay. Now, if we cannot determine the exact position or velocity, that means we will have some kind of error, right? So delta x, x is for position. This delta sign is for the error in position into the error in momentum. Momentum means mass into velocity. Mass is constant. That means it is essentially the error in velocity only. Now, the product of error in position, the uncertainty in momentum, and the uncertainty in position is greater than or it's equal to h upon 4 pi. This is equal to h upon 4 pi. That means we will have some kind of uncertainty which will be greater than or equal to h upon 4 pi. Now, what is delta x? The error in the measurement of position, that is the uncertainty in position. Delta p is uncertainty in momentum. Okay. Now, if I write this, it can be delta x dot m into delta v, which is greater than or equal to h upon 4 pi. We can also say delta x dot delta v is greater than or equal to h upon 4 pi m. H upon 4 pi m. Here delta v is equal to uncertainty in velocity. This is the Heisenberg uncertainty principle.
Done, sir.
All of you done?
Yes, sir.
Yes, sir.
Okay. Now, write the last part, that is the wave mechanical model of an atom, or quantum mechanical model of an atom. Quantum mechanical model of an atom. Okay. Now, there are a few points of this quantum mechanical model, and I mean, there are multiple points, but you have to learn and remember only a few points. Okay, only a few points. Write the first point regarding the quantum mechanical model. Please write with me. This model wave associated with electron. This model gives the idea of wave associated with the electron. Next point. It gives the 3D wave associated with electron by the following equation, which is a long equation. You don't have to worry. It's d square psi upon dx square plus d square psi upon dy square plus d square psi upon dz square plus 8 pi square m e minus v psi is equal to 0. It is equal to 0. E minus v psi, it is equal to 0. Okay. Now, what are these x and y and z? These are the coordinates x, y, and z, and this double d square and dx square, this means double differentiation. Okay, it just means double differentiation. What is this psi here? So let me first write what are these x, y, and z. These are the coordinates. Okay, these are the coordinates. What is this psi? It is the wave function. Okay, wave function is the amplitude of wave. E is the total energy, and the last V is the potential energy. The potential energy. Okay.
Yes, sir.
You don't have to learn any of these things. You just have to remember this thing, that psi is the amplitude of the wave. Okay. Psi is the amplitude of the wave. Now we have to learn only things about psi and then psi square. Okay. You don't have to learn anything. You just see that there is this equation. From this equation, we have to point out only one thing, which is psi. What is psi? What is psi? Psi is
Function.
amplitude of the electron. Okay, amplitude of the wave that is associated with electron. Amplitude of the wave that is associated with electron. Psi is the amplitude of wave associated with electron. It does not have any physical significance. It does not have any physical significance. But if we have psi squared, we have psi squared. Okay. If you can remember from this chapter Sound of 10th standard, amplitude square is intensity. Yes, intensity is amplitude square. No, you don't remember? Okay, if you don't remember, that's fine. But you should remember, you should know that amplitude square is equal to intensity. Okay, since amplitude square is proportional to intensity, since amplitude square is proportional to intensity, hence psi square gives the probability of finding electron at a particular coordinate. Will give you psi square will give you the probability of finding electron at a particular coordinate. Okay, hence psi square has physical significance. Psi square has physical significance. Psi square is also known as probability density. Let me know if you're done with this one.
Done, sir.
Done, sir.
Okay. Let us someone else in chat. Okay, is also there. Okay, so this is it for the structure of atom. This is it for structure of atom. Okay, now you have your next class. You may have tomorrow. You may have 1 hour class tomorrow, but it's not confirmed as of now. So till Monday. So this is Wednesday, Tuesday, Thursday, Friday. We have Friday and Saturday, somewhere holidays, weekend, then Sunday, then on Monday. Okay, so on Monday we will start with the periodic properties chapter, and what I expect is that you complete NCERT exercises of chapter 2. Okay, complete the
Okay, sir.
NCERT exercises of chapter 2. Okay, try it, and if you have any doubt, okay, if you have any doubt, take a pick of question and send it to Nishkarsh sir at any time. Okay, we'll send that picture anytime if you have any doubt. Okay, If you have any doubt, I will send you the answer, but I will not solve the complete answer. Okay. So what I will be doing is I will be writing a few statements that may help you understand and give you a track on how to approach that question. Okay. But even then you cannot solve it, then I will solve it and explain it to you also. Okay.
Okay, sir.
So can I expect everyone to complete chapter 2 in CERT exercises?
Yes,
sir.
sir.
Yes, you all will try. There are many questions. Okay, can anyone imagine how many questions are there in CERT chapter 2? Any guess?
Sir, I think it's 67.
Yeah, it's around 670 questions. Okay, so it's okay if you don't do a few, but try to at least read all of them. Okay, and if you think
Yes,
sir
sir.
ये तो सर ने नहीं पढ़ाया लगता है ऐसा, if you get some that kind of